Hello students, in this video we'll discuss nonlinear first-order differential equations which are explicitly solvable for the derivative. So let's consider a first-order ODE. And this ODE is going to look like what? Our general form of an ODE is f of x, y, and then y prime is equal to 0. That's our general form of an ODE. But let's suppose that we can actually break this ODE up into a whole bunch of different parts, or we can like factor the ODE. If we can factor the ODE, if we can factor this, as a function of y prime, and typically what happens in these sorts of problems, we're going to call y prime p, okay, just as a variable. So what we want to do is we'll have our equation over here, so our f of x, y, y prime, I'm calling that p equals 0, can be factored in some sense into f1 of x, y, p, all the way down to fn of x, y, p equals 0. I might have n distinct factors over here, and if we have n distinct factors, if we can solve each of these individual factors, if we can find solutions phi of x, y, c, I'll call that phi I of x, y, c, to the equation fi of x, y, p equals 0. If I can find the one parameter family solutions to these individual factors, then the general solution of our original problem of f x, y, y prime equals 0 is the product of these terms, is phi 1 x, y, c times all the way down to phi n x, y, c equals 0. So let's see an example of this. So what I'm going to do is the following. I'm going to solve. I'm going to first like this y prime squared, and then minus, or let's do plus, x times y, y prime, plus x times y is equal to 0. There's my first order differential equation. Now I'm going to treat the y prime as a variable p, and we're going to solve for p. It's a quadratic equation. So we're going to write this as p squared plus x plus y times p plus x times y is equal to 0. And in this particular example, I've made it very easy to factor. So I can factor this as p plus x, so p plus x, and then p plus y is equal to 0. Okay, and we can just double check that. I get a p squared, I get a px, I get a py, I get an x times y, I get every term I want over here. Now each of these individual differential equations are both easy to solve. So the first factor over here is just saying that p is equal to negative x, and the second factor is, or p is equal to negative y. Okay, so this is what? This is y prime, so this is dy dx, so dy dx is equal to negative x, or dy dx is equal to negative y. And we know what the solutions of each of these individual differential equations are. The solution of this first differential equation over here is just y is equal to negative x squared over 2 plus c. That works over here. And then this solution over here is y is equal to a constant c times e to the negative x. So I just solve each of those individual differential equations separately. And so now I just set them each of the factors equal to 0. So the first factor I'm going to get over here is I will have a y plus x squared over 2 plus c. And in fact, we can just multiply by 2 to make it look a little bit nicer. Y squared is therefore, or 2y is therefore equal to negative x squared plus c. Okay, and so what's our general solution to this problem? So the general solution to our problem is going to be what? The general solution is going to be 2y plus x squared minus c. That was the first factor when I said that equal to 0. And the second factor over here is going to be a y minus c e to the negative x. I set this equal to 0, and I found the general solution to our nonlinear first order differential equation by using the factorization of the ODE as a function of p. If this is possible, the general solution will always be the product of the solution sets to the individual component factors set equal to 0 when you multiply them. Thank you very much.